on a kinetic study in the sense that basically we use kinetic gas tracer to see what's going on. And so before I start, I'd just like to follow up with an acknowledgement as well, and acknowledging actually two parts. And so for one, Queen's University, my host institute is situated on the traditional territories of Anishinaabe and the Haudenosaunee territories. And of course, the place where I'm still currently physically resides and where I've actually been living for several years doing my PhD is situated on traditional land of the Lekwungen, Songhees, Esquimalt, and Wasanic territories. And the background is actually showing a really nice map from one of the websites called the Whose Land. Actually, there's no .com, it's whose.land website showcasing where the different indigenous tribes are in North America, as well as several other parts of the world where there's data. And just, so I encourage you to check it out and reflect on which land we're situated on and our relationship with the people there, and learn just from their relationship with land. And of course, as we go on with our exploration of the cosmos, recognizing that this is a very human endeavor, and it is ultimately about learning about our place in the universe and with other people. And so with those acknowledgements, I will go ahead and start talking about the science I've been doing. So one of the classic pictures that has been shown over and over in often in textbooks and say Astronomy 101, it's that stars form in molecular clouds, and specifically stars form in dense cores where we in the simplest model is basically the self-gravitating, almost spherical body of gas that then can undergo collapse to form into a basically collapse into a central object when it's gravitationally unstable. And so there's this evolution progression of simple idea that you collapse, and because of conservation and angular momentum, you start to form a central disk, and of course you form protoplanetary disk, and then you can go on to form stars, planets, and life as we know, and eventually burning means. But one thing that we often ignore in these very introductory, oversimplified picture is that stars, star-forming clouds are actually fairly structured. So if you zoom out a little bit, you recognize that these star-forming cores are actually found, often found in these filamentary structures. And they're kind of much like beads on a wire when you look at them observationally speaking. And if you take another step back and look at the whole structure of molecular clouds, you realize filaments don't actually live in isolation as well. And the molecular clouds are very hierarchical in the sense that you have molecular cores being embedded mostly in filaments. And of course, filaments are embedded in molecular clouds that are fairly complex in terms of how it's structured in the network. And it turns out that's actually fairly straightforward to produce in simulations in the sense that if you have a molecular gas and you stir it up with basically turbulence inside, even without self-gravity, you start to get these fairly filamentary structures. And as you add more realism in the physical ingredients, like you turn out self-gravity within the gas, you can even toss a magnetic field, which turns out to be important in star formation, you start to get these fairly realistic looking simulations. And one of the efforts that has been done recently, it's with the advent of large-scale survey that's highly sensitive to large dynamic gas gas range, like the top left panel, which is a real observation taken by the Herschel Observatory. We can start to compare with simulation on what are the important basically physical processes and forces playing beyond star formation, and how strong are they relative to each other, as well as how do these clouds evolve as time proceeds, kind of so to speak. And so a lot of work actually has been done at simply comparing the structure. Either you do some sort of power spectrum analysis, probability density distributions, or sometimes people measure filament width. And most of the work that's been pushed so far is actually comparing the morphology. So what's the projected surface density structure of these gas clouds? But one thing that has been looked less is that the cloud itself is inherently dynamic. And if you can actually trace the gas motion with kinematic tracers, rather than, for example, the thermal dust continuum that only give you structures, you can learn a lot about how these filaments have formed, evolved, and eventually forms cores and collapse into stars. And so what's shown on the left, it's a fairly simple numerical simulation where you have this almost cylinder-like filament structure, and then you just let gravity do its job, and you see these fairly well-ordered accretion onto the filament that's mostly just perpendicular from all directions. And sometimes if you do a little more realistic simulation, you add magnetic field and more turbulent, realistic turbulent spectrum, then you can see that there's evolution dependence. For example, that you have the gas flow that flows along the magnetic field line shown in purple. And as you progress down the each row, which shows the time axes, you have, of course, a filament that just forms in the middle and it gets more concentrated by accreting material along the magnetic field line. And once the structure is actually dense enough, you also see that you start to drag the magnetic field line towards the structure and distort it. And the flow which follows the magnetic field line start to get actually distorted. It's no longer this nice kind of fairly smooth, smooth flow in the large scale, so to speak, kind of situation. And so the key now we're trying to push forward in these studies is, in addition to using that thermodynamic emission that tells us a lot about structure, what can we learn about the gas dynamics? And to do so, what you need is molecular line emission, because by using the line emission's Doppler shift, which of course have fairly well-defined centroid that you can basically resolve to a fast spectrometer, you can get the line of sight velocity information, and they give you velocity dispersion as well as velocity centroid of how the gas are moving. But what kind of molecular tracer you want to use, you have to be actually quite careful of which species you use, because for one, molecular hydrogen is actually fairly invisible in cold molecular cloud, where it's typically between 10, well, it's tens of Kelvin, so to speak. So molecular hydrogen doesn't really emit much light unless you are looking through much higher column density beyond simply molecular clouds emitted by structures. So one of the common tracer as shown in the middle is the carbon monoxide, often actually used a lot in extragalactic star formation studies. But as what has been shown empirically from observation, as well as in this case shown in the simulation, even when you have true surface density from the simulation and do a chemical network post-processing, some radio transfer, you realize that a lot of CO, for one, are depleted in the denser structure, and two, often they actually become optically thick. And so you're mostly only chasing, one, the more diffuse the structure, and also usually the surface layer that's closer towards you. And so it's problematic, even though that CO is very bright tracer, you actually have these constraints. And sometimes you just have to proceed with what we call denser tracers, where chemically it's more favored to be produced, one, inside denser structure, and two, they're only excited by the higher density, basically higher collision rate in higher density environment. And for example, HCN showing this simulation here start to preferentially chase the denser structure that you found in the simulation. But you have to be careful in the sense that even from this simulation paper from Presley and Whitworth, 2020, even HCN itself could become optically thick, and you actually have to go forward with even denser tracer like ammonia and N2H+. So this is actually where the Green Bank ammonia survey, co-led by Rachel Friesen from University of Toronto, as well as Jaime Pineda from the Max Planck Institute. It surveyed a lot of nearby molecular cloud within 400 parsecs or neighborhood where filamentary structure that form star are fairly well resolved. And so as comparison on the very left, it's shown the Herschel-derived column density, showing what the gas structures is. And the protostars are showing the star symbols. And you can see that within these high contour regions, most of the protostars are found in the densest gas, which is unsurprising given our physical understanding of how stars are formed. And when you look at the integrated intensity of the ammonia emission, you realize that ammonia only preferentially chases the densest gas, where you mostly forms a star. And that makes ammonia actually a really nice tracer because it directly traces the gas that eventually collapses into stars. And also you remove a lot of contamination from the foreground, background gas. So you really can just focus on the gas that's basically about to form stars, so to speak. And so that makes the ammonia survey with the green band, known as gas, a really good data set to proceed for that study. And that's actually what I focus on for a good chunk of my dissertation on. The one challenge is that even with dense gas tracer, the fact that molecular clouds are 3 dimensions, that you would expect at least some structure to overlap along the line side. And depending on the motion of these structures, you could easily have multiple components of velocity structures, which manifests into multiple components of spectral lines. And so ammonia, for one, as a heads up, is that you actually have these hyperfine structures due to the nuclear structures of the spin structures of these molecules. So most of these peaks are actually just from a single component. They're not kinematic structures. But once you basically model that, you will still find that even in a place like NGC 3033 in Perseus Cloud, for example, many places where you detect ammonia emission, which is shown in the black contour line on the right image. You also have regions shaded in blue where one component modeling is insufficient, and you would really need another component, which is shown in orange on the spectrum on the left, to model these things. In some places, you have these fairly broad line widths, so a high velocity dispersion structure that seem to be chasing more turbulent, more ambient diffuse gas. And in some regions, you actually have 2 narrow peak components that seems to suggest potentially you have 2 flows converging along the line side. So even with the densest gas that does not have a lot of foreground and background contamination, you still have to be careful of spectral modeling. And so one thing that I did for my dissertation is coming up with a tool to fit ammonia with 2 component spectrum automatically with statistic tools, and that is actually available on GitHub known as Mufasa. And once you actually have this spectrum, what you can do is you can reconstruct cleanly the velocity and spatial structure in what we call the position velocity space. So you have the on-sky spatial coordinates on the RN deck, and of course you have the velocity. And you can see that we have these complex 3D structures of basically body gas moving and forming these structures. And next thing we want to know is, can we find these filaments in these 3 dimensions? And so another thing that I implemented in my dissertation is a filament finding technique that basically places a bunch of walkers on n-dimensional density field, much like illustrating this 2-dimensional map. And then you iteratively basically allow these walkers basically to walk up the gradient in the density field until they find these 1-dimensional ridges. And so as visualization theory 3D, basically it walks on the ridges in any n dimensions. And I've implemented to run on images, and that's also publicly available as a Python package known as Crispy. So by running these filament finding techniques, we can basically look at these 3-dimensional structures, say, okay, where are the filamentary structures in our observed ammonia spectrum? And from there, this is the result that we found in NGC 1333, where we have these fairly filamentary structures throughout this star-forming clusters. And for the most part, you can see from the blue, which shows the velocity centroid, that they're actually fairly velocity smooth structure. They're fairly continuous. And often, interestingly enough, they have these very linear gradient in, for example, filament B and I, as well as sometimes you have filament A where you have a band which seems to suggest maybe you have a gas flow that converges into a point where there could be a star forming or cluster forming, so to speak. And the orange is simply showing velocity dispersion, what's the internal motion within the structure. And the other thing we can do out of the velocity centroid information is we can ask, what is the velocity gradient like? And because we have 2-dimensional map, it means the velocity gradient is inherently 2 dimensions. And we can basically find velocity gradient as a vector field. But in addition to the orientation, each velocity gradient also have magnitude. So how do we actually better analyze data to get a sense of, do we see signature of accretion flow onto the filaments or along the filament that may be transporting mass or fragmenting into cores? So one thing we can do is basically we can reconstruct the vector field that's perpendicular. So what's shown in panel A in the center is that you have a skeleton of where the filament is, and you can construct the vector field that basically diverges away from that. And if you do a clever rotation, you have the figure B, where you have just a vector field that is geometrically parallel to these filament spines. So by having these two perpendicular and the parallel vector fields, when you take the dot product of it with the velocity gradient, you can actually decompose the velocity gradient field into two principal components relative to the geometry of the filament spine. So it tells you what's the velocity gradient like, what's its perpendicular and parallel component like. So by doing so, what's shown here in the center panel is the velocity gradient measured that is parallel with respect to the filament spine, and on the right, perpendicular to the filament spine. And the velocity central map that's used, it's actually shown on the left. And of course, the nice thing about using CRISPR and doing in 3 dimensions is that you see, for example, filament C and H, they overlap quite a bit spatially in the sky, but we can disentangle them and do the velocity analysis quite cleanly. And so the box is just simply showing the structure that is overlapping on the plane sky for a cleaner separation. So the next thing is in the perpendicular component, for example, we see actually a lot of these structures. And interestingly, if you look closely, the larger velocity gradient tend to be further away from the filament spine. And that's actually a little counterintuitive from the free fall model, where if you assume the gas are not interacting with each other, and you just have free fall to the center of the filament, you're actually expecting the acceleration to increase. And for that reason, you actually expect the velocity gradient to be larger in magnitude. But we actually see the reverse in this case. And it seems to suggest a different physical process. And of course, suggesting that in this dense environment, the gas within the filaments are self-interacting. In a sense, you may be unfolding onto the filament, but once you basically enter dense environment, it actually have to be damping each other and basically self-supported by pressure rather than just collapsing in free fall kind of scenario. Another interesting one is if you look at the parallel component, you don't actually see a very smooth flow as you would naively expect from a large-scale structure of a cyclical flow onto a point, but often you actually have these interesting, almost quasi-periodic stripes. And there has been theorists we've been talking to that seem to think that these may be results of these magnetic waves, basically acoustic, driven by the coupling of the gas and magnetic field in these filaments. And that itself has some very interesting implication on the filament formation process. And because we do have the orientation, basically information as well in the vector field, we can also ask, are these orientation fairly random in each filament? And so as illustrated in these polar histograms, in many filaments, you actually have these preferred directions of how the velocity gradients are oriented relative to the filament spine. So by convention, 0 and 180 is actually parallel, so along the filament. 90 degrees is actually away from the filament, and negative 90 degrees into the filament. And so in some cases like filament G, we have fairly unimodal and largely parallel-ish kind of velocity gradient. But in some cases, for example, like filament I and J, you actually have less clear picture, but you have fairly distinct bimodal distribution. And one of the things that we need to push forward is start comparing these observations or simulations to get a sense of, does this tell us a story? For example, you have filament that, accretion flow that's mostly perpendicular on the outer skirts of filaments, and it basically changes direction once you enter the filament to flow along the filament kind of deal. But the neat thing is these orientations are not randomly distributed, and they actually show strong directional preference. So the next thing we can do before we start to do the statistical analysis of across different star forming region in the nearby molecular clouds, let's take a look at some case study on what happens if you observe high resolution. So it turns out even though gas survey usually are quite good at resolving, at least marginally resolving filamentary structures, when you actually observe with interferometer at higher resolution, for example, in Perseus B5, you start to realize that what seemed to like mostly maybe two different structure, it consists of actually a few narrower substructures. And by looking more detail at it, by doing the velocity analysis, we can actually start to look at what's the velocity gradient vector field look like. And so what's shown here is the visualization with line integral convolution technique, just kind of showing what does the velocity gradient look like in the structures. And so when you overlay with integrating intensity structure, you see that the filament, so the velocity gradient fields within the filament seem to be fairly ordered, but they're not consistently throughout the filament length, that they actually do changes a bit. And depending on the density, they also actually have a slightly different behavior. And if you look at the magnitude of velocity gradient, you also find that there are this interesting band stripe structure in terms of magnitude. And even when you have highly well-resolved structure, that magnetic field, sorry, the velocity gradient fields seem to be well-ordered, but have complex structure that still suggests that turbulence started to continue to play a role even in a smaller scale. And so one thing we can do, and I apologize that for some reason the resolution of this image is quite degraded. But one thing that often has been done in terms of these studies, so you can ask a question of what's the filament width? And one thing that has been found with the Herschel studies is that filament width seems to be about 0.1 parsec in width in general. And a lot of theorists have pointed out that that seems to be consistent in the sense that when you have these supersonic clouds and they're converging, the transonic scale happens basically typically about this 0.1 parsec scale. And that's how you form filaments. That's the natural scale in which the gas is incompressible, and that's how you fill the structures. So with high resolution data, the first thing we can do is ask a question, can we actually do similar kind of analysis? And with CRISPR that identifying the filament spines very precisely, you can actually do that quite cleanly. And by using those seeds to also actually just kind of divide an emission based on the saddle point, what's the local minimum saddle point between the emission structures, we can actually cleanly separate the regions and do the radial binning of what's the radial intensity relative to the radial distance. So if you assume a constant abundance of the ammonia to the gas ratio, then we can say what is the density, surface density structure. And one thing that we found that's actually quite interesting in the high resolution data is the fact that the filament width is actually tends to be about a third narrower than what's measured with thermodust continuum. And also we actually can fit one of the parameters, which is part law slope. Basically these tail end of the distribution ask, are they consistent with a hydrostatic cylinder? In turns out that most of these filaments are do depart quite a bit away from these toy model of hydrostatic configuration, and seem to suggest that these are quasi-static, probably dynamical structure that's somewhat in equilibrium, and they're both either contracting as well as actually accreting gas ongoing, so to speak. And anything we can measure is what's the velocity dispersion? Because if you have radial accretion, for example, one thing that you could expect is you drive accretion from the kinematic energy released through as things fall into the gravitational potential. So there's question is, do we actually expect to see an increase in velocity dispersion, as well as do they also dissipate on a quick time scale? And what's fairly interesting, even though that these filamentary structures seen, even though they're narrowed, they're mostly actually subsonic within roughly the same scale, the 0.1 parsec scale that the theorists have mentioned, probably why and how you form these filamentary structures do seem to actually conform roughly the same. So the shaded region actually shows the velocity dispersion where the internal motion is subsonic. And we can see that the transition point roughly happened around 0.1 parsec. But what's more interesting and never been measured before with high spatial resolution, it's that you actually see a decrease of velocity dispersion that's going towards filament spine. And there's actually a few theoretic models that looks into why you may potentially have that. And it turns out that a lot of the accretion model can drive turbulence, but some of the turbulence may not actually provide you radial pressure support to support the filament against its self-gravity. And in those models, you may actually see a decrease of the velocity dispersion due to the signature of these models. And so being able to measure velocity dispersion precisely as function radius also help us to constrain what kind of accretion model and what kind of modes of turbulence are actually driven in these filaments. And that gives us a better idea of both one, the filament stability, and also the formation mechanism. And also, if we do similar analysis of breaking the velocity gradient into its perpendicular and parallel components, showing the left and center panel, as well as actually showing the just simply magnitude on the right, we see that even on a smaller scale, about the 0.09 parsec scale, we still see a lot of structures. In some cases, for example, in the perpendicular structure, we have these very elongated compact structure that runs parallel to the filaments. And in some cases, the naive interpretation right now, before we compare with synthetic observations of simulation, is that these may be indicative of perpendicular accretion flow onto the filament. And when you actually accrete perpendicularly, you can actually drive these eddies that have axis parallel to the filament spine. So the velocity gradient right now is actually looking at these what we call macroscopic turbulence, so larger scale turbulence that have these eddy modes that have axes that run parallel to the filament spines. And again, these are quite groundbreaking in the sense that we never actually really, the literature our field haven't really actually looked into the spatial distribution velocity gradient, especially at highly resolved scale. So this would be a productive avenue to go forward and understanding both, the role in terms of turbulent filament formation as well as the role of accretion. So taking a step back, now that we have delved quite a little bit into the details of partially trying to understand what velocity gradients can tell us about the filaments, is let's do a more larger sample size statistical study of what's happening. And so what's shown here, it's the Herschel, actually 250 micron thermal dust emission map shown in the background. The dashed line shows contour of the gas survey, basically footprints where ammonia are observed. And then the solid black contour shows where the emissions are detected, as well as blue shaded region shows where two components are needed. And even in some of the lower mass star forming region, realize in the densest gas, two component gas are actually detected. And again, emphasizing the importance of needing to fit more than just one spectral component, which have often been standard fitting in our field up till recently. And similarly, in the eastern part of Perseus Cloud, we have the B5 region that was shown with the high resolution study, as well as IC340A. And so one thing that we can start doing is basically plotting the median velocity dispersion of these filaments against what we call the mass per unit line. So if you take the total mass of the filament and divide it by the unit length of the filament length, you can get this measure that give you a sense of the stability of the filament. And so when you plot these two quantities, you quickly realize that for one, there seems to be a positive correlation, and it's actually statistically robust when you do the basically correlation statistics, that there's a statistically significant trend correlation between the two. And it seems to just suggest that the more massive, and so, well, the higher line mass filaments, which presumably are the ones that have accretion more mass or more evolved ones, seem to have more velocity dispersion. And the simple interpretation is that that's probably due to the accretion-driven turbulence, that the longer the accretion the gas, the more basically stirred up gas you have inside the filament. So there's that correlation. And we can also see that it seemed that earlier in the evolutionary stage, most of the internal motion are subsonic, and that conforms to the notion, the theoretical picture where filaments are formed in these subsonic regions by the compressive mode of the turbulence. And one thing to note is that the typical critical line mass, if you only consider thermal pressure support, assuming you have the 10 Kelvin gas, which is the typical temperature for the coldest star-forming filaments, empirically speaking, it's that all of these line mass actually lie about 16 solar mass per parsec, which is when you expect the filament to be unstable and they would be contracting or fragmenting into dense cores. But another thing you can say is, let's naively assume the turbulent component of the pressure of the velocity dispersion is actually also contributing to thermal support. Then we can actually add additional support in the sense that we have this transcritical stage where filaments may not be collapsing radially, but they can fragment into cores, as we've seen basic cores being found on like beads on the string in filaments, as well as we can actually have supercritical stage where you no longer actually have the fragmentation of the straight along the filaments no longer fast enough that you're dominated by the radial contraction. And so this would be a fast collapse of the filament into its axis, and probably basically it sets the upper limit of lifetime scale. And so we can quickly see that there's actually a lot of filaments that are in the transcritical stage where you can proceed to form filament. And potentially sets the mass scale that may translate into the initial mass function of what's the mass distribution of the stars that forms all these filaments, as well as supercritical stage where mostly your accretion mass onto the filament, but you no longer continue to actually basically form new cores. You kind of stop, so to speak. And another thing we can actually plot is basically what is the velocity gradient in perpendicular direction as well as parallel direction relative to the velocity dispersion. And so interestingly, we actually see the correlation between both, which again goes to support the accretion-driven turbulence kind of picture, where the more accretion you have, potentially you see actually more velocity gradient, both because of you're chasing the large mass flow as well as the macroscopic turbulence stirred up in the filament itself. And that in turn basically increases the internal motion as the turbulence cascade down to the scales that you cannot resolve spatially. And going back to the notion of trying to understand how exactly do you form core in the filaments, it's that another thing that's been a focus in our study is how exactly do filaments fragment into these cores. In the simplest model, they seem to happen quite periodically, and you could be dependent on simply just the basically the width and length of the filament or other factors as well as you increase complexity. So being able to get a sense of what's the average spacing between the filaments and the number of filaments is required that forms the cores that forms in the filaments is quite important. And so one thing that we can do as a simple statistic is we can take the number of cores we found from the Herschel thermodynamic mission, and then we can ask questions: how many cores we found per unit length, basically, and the inverse of it gives you a sense of what's the average spacing between the cores. And we plot against the line mass, which, as mentioned before, could be a proxy for evolution of filament. And we also found statistically significant correlation between the two that seem to suggest that the more evolved the filament is, you actually seem to have more core. And that's actually counterintuitive to some of the simplest models that suggest that the number of cores you produce is set before you reach the supercritical or transcritical stage. It's only in the subcritical stage that you actually determine the fragmentation length. So this shows that the simple analytical model probably it's insufficient, and you really have to look at more realistic simulation. And similarly, we can also take a look at the embedded young stellar objects. So instead of cores that haven't necessarily formed a star yet, we look at the stars that's produced. and that's spatially found on the filaments. And we also find similar kind of correlation between the evolutionary epoxy, the line mass, versus the number of young star object per length. So there seems to be an evolution dependence on the formation of both core and young stars on the basically the critical mass, line mass of the filaments. And so those are basically some very interesting results, and things that I'm hoping to move forward next is, as I've alluded early on, is that magnetic fields seem to be actually quite important to the formation and destruction in the molecular clouds. And that's partially due to that the magnetic field strength is comparable to gravity and turbulent energy on actually many scales in which these dense structures are formed. So what's plotted here is the Perseus Molecular Clouds that I've been showing throughout my study. And what's shown in the background, the Planck measure magnetic field on larger scale. And with some of the recent study with the JCMT, basically polarization studies, we can actually start to measure magnetic fields on much more smaller scale within the filament. And so what's shown here is NGC 1333 in this basically shown in this white contour region, which I've also been studying. So the next thing I'm hoping to push forward is to get a statistical study. How are the velocity gradient correlated, or if they're basically correlated with the magnetic field, and what does that say about the role of magnetic field in assembling gas from the larger scale all the way down to the smaller scale that you can go onwards and form cores. And so on that note, I'm just going to leave the summary slide here and point out the three takeaway point is that even with the densest gas tracers that only trace the star forming structures, you really need to be careful about how you do the line fitting, because often you actually have more than one line component. And so you really have to deal with that carefully to make sure that you do not have contamination and you're not overestimating, for example, the velocity dispersion by erroneously fitting just one line component. And by disentangle these multiple components, we can actually then proceed to make velocity gradient measurements in these dense filaments. And what we found both on the 0.05 parsec scale and even smaller is that velocity gradient is highly complex. We don't have this simple, smooth kind of story where we just have smooth gas flow onto the filament along the filament. It turns out that the turbulence continue to play an important role even on the small scale. And so the next part is to reconcile that with the theory and trying to understand what's the role of turbulence and what does that say about the accretion process in the formation of evolution filaments and cores. And then lastly, we also realized that when we consider mass information, that dense filaments that are forming stars are mostly thermally supercritical. And so they're in the stage that they're ready to form dense cores and stars, specifically stars. And based on analysis done statistically in the nearby molecular clouds is that they seem to be growing by accretion. And that seems to also, in turn, drive additional turbulence within these structures that potentially give them some support by time to grow further before they completely collapse and form stars. And so on that said, thank you for listening, and please let me know if you have any questions.
Thanks, Mike. That was really good. Your beautiful figures reminded me a lot of Jan English's Keelak lecture during Casca, which I think a lot of us saw. Really nice. So there were a couple of questions in the chat that came up. I saw the first one I saw was from William. Do you want to go ahead and unmute yourself and ask that?
Yeah, actually, I have, if you're going to include those, I have a lot of questions. Maybe you can go to the chat questions later, but I would like to ask two now, if I might. My first, well, one of them will be about the dispersion line mass correlation that you talk about. I'm always very skeptical of correlations. But before we do that, can you show your velocity gradient diagram with those little stripes in them?
Mm-hmm. Let's go to, yeah, NGC 1333.
Yeah, I mean, you mentioned that some kind of magnetic effect. I think you said magnetosonic waves can produce where you have the like the reds and the blues together, and it's not large scale. But I'm wondering, wouldn't that also be an indication of collapse on a smaller scale, like little clumps within the filament? Doesn't it represent collapse like that?
Yeah, no, that's a very good point. And that's one thing that I forgot to mention that. So we did try to basically see if there's correlation between the dense structures and these basically high velocity gradient region. And unlike one of the study, which weren't really replicated in many other follow-ups or similar studies, we didn't find correlation between these quasi-periodic stripes and where basically the cores are found. And so at least in places where we look spatially, we haven't found correlation, but that's a good question in the sense that that's naively what we expected first. And the fact that we didn't see correlation between those seems to suggest there's alternative reasons why they exist.
Yeah, color me naive. Yeah, can you go to the dispersion line mass relation you had? You said there was a correlation there, statistically significant. You see, the problem I have with a diagram like that is it's the range and the axes. It's like less than 1 order of magnitude, 0.7 dex or something like that at most. And I'm thinking if you get more observations and some of the points don't go in what you would call the right places, you ruin that correlation. So I'm wondering, I mean, if you get higher resolution observations, can you increase the range in your axes to get more than an order of magnitude? Is that what you're looking for?
So in terms of the basically y-axis is what your main concern is?
Yeah, the range in the axes, because I mean the smallest to the largest, it's less than an order of magnitude. And if it's more than an order of magnitude, and that correlation holds, I'm guessing it would, but it would be nice to see that.
Yeah, no, that's a very good question. So for one, it's rarely, I guess there's, yeah, I think you pointed out that there's two important distinctions in the sense that in the larger study, larger dynamic range, there's also, yeah, science line with relationship that's usually being attributed to basically the Kolmogorov turbulence cascading like kind of relations. So this is actually in the regime where, for example, let's say a Goodman study, what we call the transition, what she called the transition to coherence, where once you get to roughly transonic regime, that line, mass line width relationship that's often seen breaks down. And for a while before we actually start to resolve at smaller scale, typically the trend seems to be it's fairly flat in size line width a relation. So it's a little different, of course, for the other audiences here that we were measuring the mass per unit line. So it's not quite the same size as a proxy. But so to give provided context, we're in a regime where basically we enter transonic regime. And for the size mass relationship, we tend to basically flatten in most study. Aside from some of the higher resolution study, you start to see those trends, but authors haven't really commented on those yet. So that's one. So increase in resolution, actually, I don't think will actually increase dynamic range in the y-axis because both from the theoretical end where filaments are formed in the transonic scale, we don't really expect basically the line width to go significantly higher. So that's one. And two is that we also have to be very careful tracers. So there's another study that have shown very similar, actually basically almost the exact same plot, but with slightly different tracers. They also use ammonia and N2H plus for their dense gas tracer, which is good because as mentioned before with CO, you could actually trace a lot of unrelated gas along the line side with much larger volume in terms of column volume. So those ones you can superficially drive the dynamic range larger, but simply because you're including a lot more larger scale gas, so to speak. And so long story short, it's that so far there's two studies that seem to suggest correlation. And you're right in the sense that with more data, we will be able to tell how robust this is. Of course, if we see more scattered, then this trend will go away, or the correlation could tighter. And so those are very legitimate concerns. And of course, the more data we have, the better. But I don't think the resolution will increase the dynamic range for that reason. And typically, it's actually if you degrade the resolution, then you can superficially drive the velocity dispersion to larger line width.
Okay, thank you.
Thank you.
Cool. Chris Matzner, I see your hand up. Do you want to unmute yourself?
I think I'm unmuted. Can you hear me?
Yeah, I can hear you, Chris.
Okay, so hi. Thanks, Mike. That's a great talk. Couple questions. they fall in three categories. So one is magnetic field, the second one is orientation, and the third one is bulk flow.
Mm-hmm.
So so first of all, with regard to criticality, have you considered criticality including the magnetic field threading the structure? For just to run through them quickly, for orientation, have you thought about the variations in orientation relative to the line of sight? And then bulk flow, and I think this is what I really want to know. Based on what you see, can you tell whether the filaments should evolve, radially on their own scales, faster or slower than they should move through the cloud and interact with one another or other structures?
Right, that's a good question. So let me try to remember. The first part, it's a support part. So no, for our analysis, we haven't really compared with the magnetic support in the sense that we can either just grab some empirical numbers in Perseus Cloud that has been measured and run that, or simply make assumptions. So we haven't done that yet. There's a paper by Schmidt et al. On the Perseus beef that I've shown with exactly the same data that Jaime Pineda has taken. So those one, they have looked into the magnetic field strength, at least as the upper limit, and they did make some estimate on whether it's supercritical or not. But no, for these analyses, two things we have considered is the thermal pressure support, and of course, showing the blue shaded region is if we add the turbulent, basically non-thermal component velocity dispersion as quote unquote turbulent support. And of course, that's probably an upper limit estimate. So that's the first part. Remind me, the second question is orientation, right? So orientation, so far, no, we have not accounted for orientation. And that's why I have been reluctant to, at least I haven't ventured into calculating the mass accretion rate yet, because simply depending on the assumed geometry, it really depends on what's the mass accretion rate. So the step forward probably would just be taking a simple assumption, let's say 60-degree inclination angle as statistical average, assuming everything's randomly oriented, and do a correction on that. But it'd be interesting to start working with synthetic observation and simulation, where you have the full control of inclination angle and use that to estimate what's the expected uncertainty based on the different inclination angle. And so long story short is we have not taken that into account in our analysis yet. And so the third one, remind me, what was the third one? Your third question.
Flow along or relative to other things, relative to, on the scale of the filament widths themselves.
Right. So that is also another thing that we have not quite done analysis yet. So for one, it's that, of course, you can, for the trends that are fairly linear, as shown before, you can make a simple assumption of bulk motion and just say how long we can move. So we have not done that calculation yet for along the filaments. When we look at the resolved structure, for example, some of these perpendicular and parallel structure, and if we assume some of these are, especially perpendicular components, assuming the accretion flow, we need to be a little more careful of how do we translate what's really the line of sight acceleration field. That's what we're assuming we're measuring with this velocity gradient. How does that translate into motion? And so we have not done that calculation yet, but another thing that we have to look at is also the bulk motion. So if you look at the velocity center of each filament, we can ask how quickly are they basically, what's the relative motion between these filaments? And most of them, if I recall correctly, they're roughly transonic. And so, you can calculate, do we expect collision rate, collisions between these filaments based on those velocity and some naive assumption of separation, but we have not done that calculation. But I think that'll be interesting to look into, and appreciate your input on that.
Thanks.
Okay, one last question from Wes. If you're still there, Wes.
I am, yes.
Okay, there go.
Sorry, I was finding the mute button because space wasn't working. Hey, Mike. Good talk. The plot that you showed with the filaments and the quote unquote radial profiles from them, it seemed to me that the radial profiles you generated were just on the apparent, like actual observed brightnesses on the radial profile, right?
Correct.
Is there any worth, like if you're just looking at the filament C, for instance, you can see a large, brightness variation along the filament. Is there any worth in normalizing the brightness at the irrelevant points along the filament before creating the mean radial profiles? Because there's a lot of dispersion along A and B, for instance, in the brightness direction. I'm wondering if that would all go away if you normalize them first. Yeah, no, that would be a very useful technique. And so for some study that actually focused more on measuring structures rather than looking at kinematic and other information, I don't think people have normalized yet. And I think that would indeed help to actually resolve a lot of these dispersion. But people have done what they've done instead of doing the average profile, they fit basically each cross section. So you can imagine basically separated by each resolution element, they do a cross section and then they fit a profile. And then they talk about statistical average those profiles. So those ones would have been effectively accounted for normalization of the amplitude. But you're absolutely right in the sense that if you look at right on the filament spine, the scatter is largest. And as you correctly point out, a lot of it has to do with the fact that we're averaging along the length, and there's a dynamic range, quite a bit of variation along the length as well. Yeah, okay, thanks. Good point.
All right, cool. So that's all we have time for questions. So thank you everybody for coming today. Next month, we will have Alexa Villam from Waterloo talking about astrostatistics. So thanks again, Mike. That was a fantastic talk, and I'll see everybody next month.
All right, thank you. Thanks for coming.